Welcome to the project demonstration of advanced current limiting and power sharing control in a PV based grid forming inverter under unbalanced grid conditions. So the main purpose of this project is whenever the output load varies, then the inverter changes the output voltage, and in order to maintain that we need to use the two sections. There's two adjustments. One adjustment is grid forming and the second is grid following. So in this project we are developing grid forming technology. So the main difference between these two is based on the output voltage. When we adjust the input voltage, so then it's called grid forming, and if we adjust the input power, then it's grid following. So means whenever the output voltage is required one, so we need to maintain the input voltage. So for that purpose we need to use the buck boost converter in between the battery and the inverter. So generally the buck boost converter used to like before the battery charging section. Why? Because whenever the voltage is varies from the solar panel, so as you know that based on the sunlight the voltage and current will varies. It's a variable source, and when these two are varies, then the battery won't charge in time. So in order to maintain the maximum current with sufficient voltage to charge a battery, then we'll place this buck boost converter in between the source and the battery end. So then we can charge a battery with sufficient voltage and current. So in our project we are going to follow the outputs. So means we should form a inverter. So we should form a grid to maintain the output voltage in order to adjust the input by the adjusting of input voltage. So that will be achieved by our PIC 16F72 microcontroller by measuring the input voltage from the solar panel. So then we need to adjust the input voltage to the grid, so to form the grid forming technique. So coming to the grid following techniques, then we need to adjust the power. Nothing but it's a combination of current and voltage. Then we need to use the SEPIC converter. So the SEPIC converter is nothing but which will provide us the same polarity output with respect to the input polarities, and coming to the buck boost converter which will provide us a reverse polarity output with respect to input voltage polarities. So now the flow is, so from the solar panel, this is 12 volt 5 watt solar panel, we are providing that to the battery through this charging circuits, and to the microcontroller A0 pin through this voltage sensor to measure the input voltage. To adjust that, we are going to provide the pulse signal, the PWM signal, to this buck boost converter, the buck boost converter, and after this buck boost converter the output voltage is given to the inverting circuits. So here we are using DC to DC converter and then after DC to AC converter to utilize that in the grid applications. So coming to the charging section, there we are providing the two sources to charge a battery. One is the AC 230 volts inputs and there is a solar panel. So these two are look like same. So on this one we can see 4 diodes, those act as a bridge rectifier, and when we providing AC inputs on this charging circuit, these 4 diodes will act as a bridge rectifier to convert AC to pulsating DC. But on this one, though we are providing DC power supply, so these 4 diodes will act as a polarity corrector. Means if we connect the solar panel in reverse direction, nothing but reverse polarity, then these diodes will rectify that and provide us the output to minus to minus, plus to plus. As we know that the rectifier input is AC signal, nothing but alternating current. You can connect minus plus, plus minus, but the output of the rectifier is plus minus separately pins will get that. So that output probes given to the battery through these 2 diodes. So the diode's purpose is whenever the battery is fully charged, it will become the high potential. At the same time, if there is no sunlight from the solar panel, then it will get the reverse. If you don't place the diodes, then the power will get from the battery to the solar panel, so that the charging circuits and solar panel will get damaged. In order to protect that, so we place the 2 diodes in reverse polarity from the battery to the solar panel, and in forward direction correct polarity, not reverse direction, to the solar panel to the battery. Same on this charging circuit also. Then there is a LED indication we can get when we connect the 230 volts AC input to this power cable. So yeah, when you put the 230 volts AC, this transformer will step down the 230 volts AC to 12 volts AC, and the 12 volts AC to the pulsating DC. After the rectifier, after filtration, we will get pure DC voltage, same that was given to the battery through these 2 diodes. And after the battery is fully charged, so if you want to charge a battery from the solar panel or transformer, so it will be fully charged in duration of 10 hours. So after that, coming to the battery ratings. So here we are using 12 volt 2 amp battery. So this battery consists of two battery packs in parallel. So one battery pack consists of 3 4 volt 1 amp batteries are in series. So we will get 12 volt 1 amp, and these two are in parallel. So we will get 12 volts 2 amps. So that output is given to the microcontroller board as well as to this buck boost converter. So here using this buck boost converter in order to maintain the voltages. Buck nothing but when there is more voltage, and boost nothing but when there is less voltage to run the inverter. So coming to the motherboard. So there we can see one regulator, because our microcontroller need 5 volts to operate. So to get the 5 volts power supply from the 12 volts, this 705 regulator will provide us 5 volts constant output. So that is given as in main power source input to our microcontroller. And on this motherboard there is a reset switch to restart the microcontroller, and the steel plated one is a crystal oscillator which will provide the clock pulse to the microcontroller. So the main purpose of the oscillator is, so controller need clock pulse to execute the instructions. So in our project the instructions are read the input voltage and control the output voltage. So these instructions needed clock pulse, one clock pulse, one instruction, so that the controller execute 20 mega instructions per second, as we are providing 20 megahertz per second clock frequency. And after that, on this boost circuit, buck boost converter, there we can see one capacitor, one inductor, one diode. So whenever we increasing the on time for this, so it will coming under the boost mode, so that the capacitor inductor will be charged. And after that, when we switch off this MOSFET, the inductor will discharges. So with help of this diode, so the voltage inside the capacitor won't get back to the inductor side, because it's in reverse bias from the capacitor to the inductor end. So that V1 plus V2 will be added, and that is the output given to the inverting circuit here. So this is the on off switch for the inverter, and this is the on off switch for the whole kit. So this is on for the whole kit purpose and on off for the inverter purpose. So once the 12 volts given to this circuit, on the circuit we can see two controllers, nothing but they will act as a pulsating pulse generators. So the generator pulses means of 12 volts AC pulse are generated from this one, and that pulse is given as input to the gates of these two MOSFETs. One is the 7805 regulator. So from there we are going to charge a mobile phone also, means we can connect a USB load on these two USB slots. And that 12 volts DC is, as we discussed, converted to AC with help of these two ICs, and that given as input to these MOSFETs. So there the MOSFETs will provide the 12 volts 2 amps AC power. Generally these two ICs will provide the less current pulses, and after these less current pulses given as input to these gates of these two MOSFETs, so this will provide us the 12 volts 2 amps AC. That is the input to our step up transformer. So this step up transformer will step up the 12 volts 2 amps AC to 230 volts AC. So that is directly given to the our load. So this will form the grid one, and this is to form the grid forming and next solar based grid forming technique. So in this way we are going to form the grid based on the input voltage with respect to the outputs. So if you want to make the grid following, then we need to use the SEPIC converter to maintain the sufficient current.